Wow. Yes. Okay, so let's get started, and we'll try to get everybody out of here as quickly as we can. I have just a few things I'd like to share. My name is Chris Kaler, by the way. I'm the coordinator of the graduate projects, but I don't do anything related to the project itself. So you will be working with a faculty advisor. You're going to be hearing about the students who are on those projects. And I should remember that we're recording this. So let me stand over here. So my name is Chris Kaler. I'm the coordinator for the graduate projects. The students you're going to hear from tonight are on a project with a faculty advisor. So if you're unfamiliar with graduate projects, I'm going to give you a brief overview of about maybe 5 minutes, and then we'll get started. We'll have project overview of all the projects, not guaranteed that each one will run for the fall. I think there's 1 or 2 that are on the fence, and I'll tell you what those are when we get to them. And I will answer any questions you might have after this is over this evening. So how many of you here that are considering projects are a master's student? Any PhD want-to-bes someday? Okay. And then how many of you came for, or you're, I guess, currently at CU, correct? Undergrad? Or is anybody undergrad? Okay, great. Do you know what focus area you would be if you were in the graduate school? You don't have to answer, but all right. And do you know why you're here? I mean, you're here to learn about graduate projects, but hopefully you're here to learn how that might help you. But why you're at CU, why you're getting a master's degree, if you're trying to decide if you want to go on and do research, if you want to become a professor, something like that, I hope you're thinking about that and what you'll do after you graduate. So my goal is that graduate projects will be a way for you to achieve your goals, whatever they might be. And let's talk a little bit about what that is. So if you're going to get a master's degree in this department, there's 3 ways to get it. There's 1, you can write a thesis. 2, you can take graduate projects. Or 3, you can take a bunch of extra courses and get a certificate. There's also 1 certificate where you have to take graduate projects as well, but that's more of an exception to the rule, or not exception, but a special case. And this is open to all graduate students from all departments, but in the aerospace department, you can get your master's degree through the graduate project component. The other thing to note is that in this course, over 2 semesters, if you do that, you get exposed to project management, you get exposed to systems engineering on a hands-on research project, working directly with a faculty advisor, and in some cases, a company sponsor. So if you haven't had a lot of project team experience, this is a great way to get it. And we have many graduates who talk very highly about the experience. This is brand new. This is from a graduate project student who send this 90-second video to us to show the value it had on him.
Hi, everybody. My name is...
And you can't hear it, so hold on a second.
Hi, everybody. My name is James Mason, and I am a research scientist and engineer at Johns Hopkins Applied Physics Lab, working on and leading NASA missions. I was a student in grad projects in the 2011 to 12 academic year, and then I just stuck with that project, and it became about half of what my PhD thesis was based on. We were working on a CubeSat that ultimately NASA funded. Grad projects is where I discovered the career path I wanted to be on. We launched that CubeSat called Minx from the space station just a week after I defended my PhD. On the actual spacecraft itself, I had laser engraved everyone's names who had worked on it, and that face of the satellite just happened to be pointing at the camera when astronaut Tim Peake took pictures of it being deployed. So I literally got to see my name in space. That was the culmination of years of work I'd done that started in grad projects. I got to be involved in almost every aspect of it: mechanical design, machining and assembly, FEA, thermal modeling and vacuum testing, systems engineering, boatloads of other testing, project management, electrical assembly, ground software development, mission operations, STK orbital simulations. And you know what? I did all those things because they were fun. And objectively, it is so cool to work on a real project. Now I'm the principal investigator for a $9 million NASA CubeSat called Sunset, and I was able to pull off this leadership role so early in my career specifically because of that experience I had that started in grad projects. So I hope that you take advantage of the opportunity that grad projects provides.
All right, so take it from him if you don't want to take it from me. Graduate projects gives you an edge, and hopefully that edge will get you where you want to go with whatever
Hi, everybody.
you're doing.
My name is James Mason.
Like being
Hi,
able to
everybody.
use a computer. There we go. So graduate projects is broke up into one large lecture section. So all the graduate project students get together once a week, and in the fall it'll be from 4:10 p.m. to 5 p.m. And we have a weekly lecture, and that's it. Or we talk about different things that will hopefully be applicable to your project. And then the rest of the week, you spend that time in the course working with your team or your project with your faculty advisor, working towards a goal. One unique difference between graduate projects and other project courses, like in the undergrad world, is that you can start them at any time. You can start graduate projects in the spring and then take it through the end of spring and into fall. There's not necessarily an academic year project limit. Some projects go in one semester from start to finish. Other projects, like you'll hear tonight, have started years ago, and they're still going. So we're going to hear about each of these projects here tonight. Again, if you can save your questions for after, and then we'll get through each of these presentations, hopefully in 5 minutes each. Any questions, though, before we get started? And if you're just joining us, we have fantastic cookies up front, so please grab as many as you would like. And there's a sign-in sheet going around if you would be so kind to let us know your interest. All right, so with that, I'm going to start with first, here's our agenda for tonight. Again, we're going to try to do these 5 minutes each, and we're a few minutes ahead. So let's get started. When we have one of our faculty advisors here, the rest will be all student presentations. So Dr. Murata, if you'd come on up. No? No, not a doctor. Well, you just got an honorary doctor tonight. Congratulations. All thank.
Yeah, thank you,
All right.
Chris. That's fine.
It happens to me.
It's
all
not
the
an
time.
insult to me. It's just an insult to everyone that's got a PhD. So,
Does anyone have a PhD in here? See?
and no one's
There you
going for one. It's all right. We're good. I'm Brian Murata. Quick little background about me. I got my master's and undergraduate degrees from CU long time ago. Went off, worked on space station for Boeing down in Houston. Then couldn't really stand Houston. Sorry to any Texans in the room. And then came back here and worked at Ball Aerospace for 18 and a half years doing attitude control design. And now I'm working at LASP as an GNC lead on a deep space mission that we're working. The project that I'm an advisor for is called ACES, the Attitude Control for Precise Sciences. It's a project sponsored by LASP and the Aerospace Corporation to develop ADCS algorithms, simulations, and ultimately a whole CubeSat package that could be flown for high precision pointing missions. Currently, we had some students last semester. They worked a lot on some simulation development. Currently, we don't have anyone, so we're looking to enroll some students in the project for this next fall. And we will be looking to further advance the design to a CDR level, as well as start procuring hardware to incorporate into a flat set and start, providing students with kind of hardware hands-on experience, integrating, reaction wheels, star tracker, different sensors, different actuators into the computer, flight computer, and running that closed loop with a simulation. I think I said all that already. That's Formex. I can't stay the whole time, so if you have any questions for me now, would be a great time to ask.
If you have questions later, you can email me and I'll do that.
Yep. Forward them on. So if you have any interest in doing attitude control design, or even the systems engineering associated with that design effort, ACES would be a good project for you. So, all right.
All right, so we're going to move on. We have 4 CubeSat missions as a part of graduate projects. Each is treated as its own separate project. So you're going to hear a lot of CubeSats here for the next 20 minutes or so, and then we'll shift gears into the other projects. So first, It's that. It is recording. Okay, you're now making me freak out, AJ. So let's make sure it is recording. Zoom. Can't find my, oh, there it is. Yeah. Oh, no. Yeah. Is it saying it's recording?
Sorry about that.
That's okay.
There wasn't a light on the thing. I just wanted to double check.
I appreciate it because, yeah, we want people to be able to watch this forever and ever. Okay. So with that, we'll have our SwarmX team come up and present. Please introduce yourselves.
Sure, thank you. So hi, I'm Maggie. I'm the project manager for SwarmX. With me, I also have Zach from our systems team and then AJ from our command and data handling team. So getting right into SwarmX. SwarmX stands for the Space Weather Atmospheric Reconfigurable Multi-Scale Experiment, which is always a mouthful. So we just call it SwarmX. We're funded by the National Science Foundation, and we're actually a collaboration between 6 different schools across the US to design, build, and fly 3 3U CubeSats to meet our mission goals.
We have 3 primary mission goals: science goal, engineering goals, and education goals. Our science goals are to measure the equatorial ionization and thermospheric anomaly, which essentially is just measuring the oxygen content in the upper atmosphere, since they contribute to a lot of spacecraft decay. So we want to understand it. Our engineering goals are to do formation flying and collision avoidance. So we're going to be doing propulsion and rearranging our 3 satellites relative to each other throughout the mission. And then our education goals are to kind of expand the amount of CubeSat programs at undergrad schools across the country. So we are working with a couple different schools, many of whom have not had CubeSat projects before. So we're trying to kind of spread that wealth through CU's experience in the field.
Thanks, AJ. Yeah. All right. So our current mission, what we're doing right now, we're calling it mini SwarmX. So we're doing just 3 CubeSats. They're going to be in a string of pearls formation, flying in a line. And this will be good for local scale measurements. Eventually, though, the idea is that it'll be able to be scaled up, so we can get 9 CubeSats going for regional scale measurements, and eventually like swarms, like constellations of these SwarmX satellite CubeSats for global scale measurements to really get a better characterization of the science we're trying to do. So, but yeah. So there are 6 universities. All the different subsystems are kind of spread out to these different universities. So we're here at CU. So we're in charge of the systems engineering, the science team, the instrument team, the command and data handling, thermal, and communications. Then going, counterclockwise, there's USA, which is University of Southern Alabama. They do the electrical power system as well as communications. Georgia Tech does attitude determination and control along with propulsion. Allen College, which is up in Massachusetts, they also help with systems. But they're the lead on systems, and we also help. Yeah, we share it. They also do structures and the ground system. Western Michigan does propulsion and educational public outreach. And then Stanford is the experts in guidance, navigation, and control.
All right, so Zach just went over all of our sub-teams and how they're distributed across our schools. So here at CU, we're specifically looking to recruit people for systems engineering, thermal engineering, communications engineering, and command and data handling. So for all of those, I've sort of listed all the things here. So for systems, you will really be supporting integration and testing, and also tracking interface development. Specifically, we're looking to develop the interface between propulsion, GNC, and CDH. Thermal is really a lot of keeping our thermal model up to date and also developing test plans for thermal balance and TVAC testing. And for communications, we also have lots of communications testing coming up that we want support for. And then finally, for CDH or command and data handling, that's a lot of developing and testing flight software and embedded C. So, okay, cool. Yeah, so that is it for SwarmX. I don't know if y'all are staying around, but I will be here for the whole session. So if you have questions, feel free to come talk to me.
We are ahead of schedule, and that's a perfect time for Ben. Oh no, Duncan. Sorry. Ben's got the one that's got a lot of slides. No. All right. Thank you. Ralph.
Yes. All right. Hello. We are Ralphie. Ralphie bit of a backronym, but stands for Radio and Laser Path Agnostic Communication Experiment. I'm Duncan Bark. I'm the chief engineer, and I'm joined by Alex Nelson, the ADCS lead. So in general, CubeSat missions are often limited by a single path and frequently low rate or not as high rate UHF communication systems. So this can be detrimental for high data generation missions like scientific missions. So Ralphie aims to demonstrate an optical downlink technology, which is capable of upwards of a 1 gigabit per second downlink. And this is included in the path agnostic communication system, another technology we are demonstrating, which can do sat to ground, sat to sat communications over a networked radio, X-band, and an optical path. So this can be, these paths can be used depending on priority level and availability. And then an onboard FPGA takes in priority levels and the data to determine how it's sent. We are primarily going to be demonstrating the sat to ground capabilities for Ralphie. So a bit about the CubeSat. We're building off a lot of heritage of previous CubeSat missions here at CU. Building off of the SwarmX bus and core systems, as well as Maxwell's structure, and then utilizing a lot of the common flight software between the missions. Other infrastructure we're going to be using is a UHF ground station here at CU at LASP, and then commercial infrastructure for the X-band and networked radios, part of the payload. We're also going to be using an optical ground station here at CU for the optical transceiver. And then also flying a software-defined power controller developed by Amplified Space. So we're just over a year into development, and we're funded through the Air Force Research Laboratory's University Nanosatellite program. So in about a year from now, we'll have flight selection review, and in about 3 years from now, we will be launching.
So taking a quick look at Ralphie, our wonderful structures team made this CAD model. This is where we're at so far. Couple things I want to point out to everybody in the room right now is just the different communication relays we have. You can see the Bluefin X-band, there's the networked radio, we have the UHF antenna, and there's also the path agnostic communication system has a cobalt laser transceiver. So if you're interested in satellite communication, this is a really fun project for you. We have a lot of different methods that you'll be able to look at. And then also you can see we're flying the Exact 15 attitude control system. That's my baby. And it's a really, really high precision attitude control system developed by Blue Canyon Technologies. So we can close our pointing budget with the laser transceiver because it's a very small beam that we're going to be sending down. So another really fun attitude control system if you're interested in that. And then also we just have a lot of electrical stuff going on in CDH. So tons of stuff for everybody. Going into the payloads a little bit more, the first one Duncan mentioned already quite a bit was the Blue Cube path agnostic communication system. So that again, the highest level is the cobalt optical transceiver. It can have rates of up to 1 gigabyte per second. We're going to be going at about 70 megabytes per second, just as a first test for it. However, this one has low availability because we only have one telescope. So the next one down is the Bluefin X-band transmitter. This is medium throughput. That's about 25 megabytes per second, and a little bit more for ground stations. It's global. And then the last one is the network satellite radio that communicates with satellite arrays already up on orbit. So they're available pretty much whenever, and then those relay the message down to Earth. But that process is slow, so you can't get as big of messages through. And one of the really cool things is its FPGA on the packs can take information from Ralphie about the messages and automatically route them amongst each of these systems based on which ground stations are available. And then the last one, or the other one that we have, the other payload, is Amplified Space software-defined power controller. So the goal of this is to be able to control the power output from the power control board electronically with just a few clicks of your keyboard. And this is opposed to normal hardware modifications that we'd have to make if we wanted to test it in person. So this is a lot of potential in the future for CubeSat missions. Right now, we're going to be specifically demonstrating the charge controller, so working with the batteries and how the satellite or the solar panels charge the batteries.
All right, so a lot on the slide, but I'll just fly through it. For future work, as I mentioned, we have the flight selection review coming up early 2024. But before we get there, we have the critical design review, where we want to try and get some good hardware revisions done between this semester and the next, as well as demonstrating the maturity and progress of the mission as a whole, including the hardware. At flight selection review is when missions are selected to continue onwards to phase B and start developing flight hardware, putting it all together, and then leading up to launch. And then, so we're always actively recruiting. So we're looking for anyone who's interested for any subsystem. There are many options for participation. So we will work with you to make sure you can contribute and you get a valuable experience from working with us. And of course, you will have support from everyone. A lot of our members are volunteers, undergraduate and graduate. So everyone is welcome as well. So we're finally mostly focused on like systems engineers, a project manager, aiming for a lot of CDH flight software experience, as well as any comms, ground station, and thermal experience. But again, like I said, anyone and everyone is welcome if you are interested. So yeah, thank you.
Great, thank you. Maxwell. And if you're here as a guest and learning, there is a sign-in sheet going around. If you wouldn't mind, put your name on it and let us know your level of interest. Thank you.
Hi, everyone. My name is Ben, and I'm the chief engineer for the Maxwell CubeSat project. So I'll just get right into it. Maxwell stands for the Multiple Access X-band Wave Experiment located in low Earth orbit. It's a CubeSat built entirely here at CU. Our principal investigator is Dr. Palo. And like Ralphie, we are funded through the Air Force Research Lab's University Nanosatellite program. We're going to be completing the satellite this year and shipping it off to be launched sometime early in 2024. It's a nice rendering of the satellite. So we have two sort of issues that arise from satellite communications that motivate the main goal of this project. One is that downlinking images and other data from space can look a little bit like this. Another one is that when you're trying to pick which frequencies to communicate on in space can end up looking a little bit like this. And to give a more detailed view, this is what the frequency spectrum allocations look like, which is pretty nasty. And as you can see here, almost all of the room is taken up and there's not a lot of space for new users. So as far as the high rate communications part of the project goes, we really want to try and push the limits of high rate communication on small platforms like CubeSats. So we can sort of boost the downlink that you can see in a single orbit. Minx, which is the satellite that the person who sent in the video worked on, was only able to downlink a fraction of a % of all the data that it generated over its mission. So we're looking to push that up and try and downlink a lot of data, hopefully maybe even 100 times the portion of data that Minx was able to downlink. Also, we're going to be using code division multiple access communication, which assigns specific codes to different signals. So you can receive multiple signals at the same frequency and divide them up and differentiate between them. And that can make the communication space go from looking like this to a little bit more like this. Our other mission objectives, apart from our RF hardware, involves the chip scale atomic clock. We're going to be using that to try and enhance our positioning, navigation, and timing for CubeSat. It's really important, especially on small missions like this that don't usually have as high-tech position, navigation, and timing instruments as larger satellites would. We also have our T-Dagger antenna, which is our deployable high gain that we've received from a company nearby, MMA Design. And then we also have our own ADCS system, whereas some of the other CubeSats are using off-the-shelf ADCS. We've built ours from the ground up here. Just to give a brief ConOps, after ejecting from the launch vehicle, we go through our commissioning and deployment phase, and then into our main phase of the mission, which involves all of our communication demonstrations, as well as demonstrating the modes of our ADCS. Then we get into our experimental phase of the mission, which involves the chip scale atomic clock, as well as deployment of our T-Dagger. Here's a quick view of the satellite bus. On the left side, you can see our payload as well as the core avionics stack that houses all of our flight computers. And then on the right, you can see our communications payloads, which include the Bluefin, the Lithium-2, and then our Global Star radio. Additionally, you can see the peripherals that our attitude determination and control system uses in red and yellow. So here's our core board stack. We're running 3 flight computers. Our attitude determination and control system is a BeagleBone Black. If you aren't familiar, it's kind of similar to a Raspberry Pi, but much more robust. We're also using PIC-33s for our command and data handling system, as well as our electrical power system. And we're doing bare metal programming on all of these. So going forward, we're trying to complete a bunch of tests this semester so that the satellite can be ready for its final integration before it's shipped off. So we're testing our electrical power system, our communication system, as well as our command and data handling system before we wrap it all up in our day in the life test. So here you can see where we are in phase B on our project timeline, hoping to complete our pre-integration review after all this testing over the summer. And then we can get ready for our pre-ship review at the end of the year, where we ship the satellite off to our sponsor. They do a little more testing before giving it to the launch provider. So we're looking to fill quite a few roles on the team right now. We're looking for a systems engineer who has experience with assembly integration and testing with electronics. We're also looking to fill software roles on the attitude determination and control system. We're looking for people who have experience with C, as well as experience implementing control algorithms and software. And then for our payload and data computer, we want people with experience coding in Linux environments for our FPGA programming, which is the main computer in the payload and data computer system. And then for our command and data handling system, we're looking for people with experience with PIC microcontrollers, as well as C coding. And then we also are really looking for experience with software testing and general knowledge of embedded systems. We're also trying to fill out our structures team. And for that, we're looking for people with experience in SolidWorks type of software, as well as fabrication and manufacturing practices. And that's all I have. Thanks for listening.
There's still 2 bins of cookies unopened, so feel free to come grab some more.
Cool. Hey, everyone. I am Chad Flieger. I'm the project manager for HERD, and this is our systems engineer, Nathan Foote. Samuel Trucks is our test engineer, couldn't be here tonight. But HERD stands for the HLS, ECLS Research and Design, ECLS standing for Environmental Control and Life Support Systems. So we are working in collaboration with Professor Nabity, Stuart Tozer from Bioserve, and our research assistant, Cody Bahan, in developing an air revitalization system, which is basically an ECLS, but dedicated for removing the metabolic outputs by the crew. And we're testing it with short mission duration technologies to remove said metabolic outputs for the crew. So our mission statement, I guess those are a little thrown off. Our mission statement is to aid the ECLS application by designing and testing traded technologies for an HLS to characterize carbon dioxide and humidity removal in an airstream. Wow, these are really blown up. Basically, our project requirements are that we complete a fabrication of a small scale test bed for an ECLS, as well as conduct a test readiness review, as well as characterize the entire system and then produce tests with the said technologies that we're working with. So for our ConOps, first our pre-phase, we are humidifying and adding CO2 to a airstream, and then we'll be sensing each of the components of the airstream after each phase of the system. So this is our pre-phase where we're adding all of that. And then our next phase is where we're testing the carbon dioxide removal, which is our lithium hydroxide, which we'll talk about in a second. We'll, again, have sensors to test exactly what we need in the system at that point. And then through here, we will be using what is Nafion. Again, we'll explain that in a second. And this is humidity removal. And again, we have specific sensors to get the relative humidity after our Nafion, which is our humidity removal system. And I'll have deliverables. So basically our first semester, we were working on designing and procuring. So basically designing all of our elements and then getting them, which we're actually basically done with. We sent out a bunch of procurements this week. And then assembly and test will be the important part of the next semester. So I believe if we're continuing this project next semester, because it's a little up in the air right now, is that we're going to be continuing to test. There's not going to be as much iterative design, but we will be testing basically elements that have not been characterized by anyone. And one thing that we didn't mention that was shown in the project requirements was that we're actually drafting a journal or a conference publication about this technology to expand said ECLIS application. So let me hand this off to Nathan.
So our point design is the HLS or human landing system. And so there's a huge list of requirements. You can go Google that right now. If you just like Google HLS requirements, I believe it's -6. You can see what the current like contract for the human landing system is. And so we're trying to design to those requirements. For carbon dioxide removal, we need to keep the partial pressure of carbon dioxide in a cabin below 3 millimeters of mercury. It's great that NASA requirements have a whole bunch of different units, but it's neither here nor there. So the HLS is more characterized as a short-term life support capability. So we were using lithium hydroxide as opposed to a dual amine swing bed system that you might be more familiar with. And so our design here is a 3D printed housing for this lithium hydroxide. And you can see this is what's called a power cube from a distributor called Micropore. And air flows through these channels, reacts with the humidity and carbon dioxide in the air. The carbon dioxide and lithium hydroxide turns into lithium carbonate. And removes the CO2 from the air. I think we can go to the next one. So for removing the humidity, we're using kind of a super material called Nafion. It is an offshoot of Teflon. It is a plastic membrane that is selectively permeable only to water. It is currently being used on SpaceX Dragon and the Boeing Starliner spacecraft. And it seems to be the new approach to removing humidity as opposed to condensing heat exchangers, which is typically used on things like ISS and shuttle. And then our driving requirement there is to keep the cabin humidity between 25 and 75% relative humidity. We have a lot of sensors. Most of our cost is in sensors. We're measuring the pressure, temperature, relative humidity, dew point, and mass flow. And we're using the National Instruments suite of sensors to do that. And then we're also using the lab view. That's basically it there. So all this together gets into this kind of system. So in the purple, you can see this is the system that we are humidifying and adding CO2 to the air to simulate the metabolic output. In the green there is the CO2 removal. The big green cube there is the LIO housing that we have. In the blue is our humidity removal. You can see the Nafion tube vertically there. And then we just vent to atmosphere and take a lot of measurements along the way. This is a cart mounted design that's not shown in the current schematic. And then also not shown is the vacuum pump. We're actually simulating removing the CO or humidity to vacuum as they would on an actual spacecraft. Thanks.
Oh, you're good.
All right, medics is our next team, and we have one more after that. So thank you for sticking around. Jasmine?
Thank you. Okay, hi everyone. I'm Jasmine. I'm the Deputy Project Manager for Team Medics, and I'm here with Cody, who's our Technical Director this semester. Medics stands for Medical Emergency Designers for Interplanetary Crisis Situations, and we are the Human Spaceflight Graduate Project that is advised by Colonel Jim Voss, who flew to space 5 times as an astronaut. So going over our current project overview for this semester, the motivation for our project right now is to support the advancement of long duration human space flight, specifically to Mars. So there is a course that has been developed by professors and doctors working at CU Anschutz and in the emergency medicine department and here in the bioastronautics department. And they have created a course called the Medicine in Space and Surface Environments, MISSE. And this really bridges the gap between aerospace, medicine, and engineering. And this basically educate students on in-field scenarios. So things like wilderness scenarios that would happen, first aid training, things like that, to train students on how to perform medical treatment in remote scenarios. So our goal as a project team this semester is to design and build out a medical bay that can actually be placed in the Mars Desert Research Station, which is where students in this MISSE course actually travel to and spend a week living to perform these kinds of real life scenarios. So we're trying to outfit a module that would enable them to actually go out there and practice using medical equipment. So the name of our module is Medical Operations Module for Mars Analog, MOMA. And I'll just walk you through what we'd be looking at in this scenario. So a crew member would suffer a medical emergency during something like an EVA, and then they would ingress the main habitat that is already out in Mars. And then there's a hatch that connects the main habitat to the MOMA. And there they would have an examination table and different medical equipment, and telemedicine would be able to be administered on this patient. Treatment would be complete, and then they would egress using that same hatch and main habitat exit. So in terms of what we're actually doing this semester, so conceptually, we always have tasks that are conceptual and physical. Conceptually, we'll be completing a design. We already actually completed a design of the medical bay and the whole module that would be used on the Martian surface, which I'll be showing in the next couple of slides. Physically, we'll be designing and fabricating a low fidelity examination area. So kind of like that bed and treatment area where you would actually treat the patient. We'll also be designing and fabricating a high fidelity hatch. So we'll actually be doing composite layups this semester, lots of manufacturing work, and that will be actually used to ingress and egress that module when it's finally built. And then the last two items are to perform human factors testing on both the low fidelity examination area and the high fidelity hatch. And then this is an overview of our design concept, which we actually presented this week. So we had Cody do a lot of this, and you can see all the different components of the MOMA here in a top-down view. And then you can see it from the port side and the starboard side from here. And I'll hand it off to Cody.
Yeah, so now just talking about the human spaceflight projects course in general. So most of the time, the way Colonel Voss works the project is starting with one semester, beginning with a baseline conceptual design to reach some kind of goal with the customer. Then we do some rapid prototyping, low fidelity mockups, do some analysis on those, human factors testing, and then redesign as needed after the low fidelity mockup. And then we move on after that, after the redesigns, into further semesters. Normally they're about 2 semester projects, sometimes 3 to 4. Then we go into like medium to high fidelity mockups. So say a low fidelity mockup is like tape and cardboard to mock out an area and like roughly what something will be. Next, you would do like actually building some functional designs, like functional switch panels, things like that to test how a human would use them. And some things that are actually going to go on next semester is we're going to be building that high fidelity medical bay that we designed this semester. So this is actually outfitting a full trailer and doing human factors testing with this. So this is going to use a lot of skills like working with medical supplies for biomedical engineering, doing a lot of structural design and manufacturing specifically, human factors testing, and some things I didn't show is we're going to be working with like solar panels. So there would be solar panel design and integration as well. So that's just some things to look forward to. And this is just an example of last year, what we did with Volt, which was the previous human spaceflight project. So essentially, last spring, we started with a conceptual design of a rover, as you can see on the left side. And then in the fall, the following semester, we actually built that real life rover on a golf cart and conducted a bunch of human factors tests and drove it. It was pretty fun. But yeah, I think that's about it. Thanks.
Everybody does. So We cover a lot of different things with the different projects. So if you're looking for, again, that project management experience, that systems engineering experience, that hands-on experience, that thing that will give you an edge, graduate projects is a great place for you to experiment and consider getting those skills. Plus getting to network with companies, sponsors, and more importantly, faculty here that are doing research that is in many ways cutting edge. Again, the course itself has a lecture component that meets once a week. And there are some things there that I can explain to you later, but it is minimal amount of work, in my opinion, compared to the work you do within the project. But there are some aspects to the lecture component. Timesheets, for example, and presentations like this that you are helping spread the word about your work. The last thing I want to say is my contact information there, or just kohler@colorado.edu, or my office. But to register for this course, you do have to go through me. So it's a controlled enrollment, not because we're trying to limit who can do it, but to make sure that we go through a process to place you on the project that makes most sense in what you want to do. So with that, I think we almost nailed it. It's 7:02. So if you have questions, if the students are willing to stick around for a few minutes, we'll be happy to answer questions. If not, I will do my best to answer them. Please grab some more cookies before you leave. And thank you for coming tonight.